All right, welcome guys. What we're going to be talking about today is electric potential difference and the flow of charge. What you need to know before watching this video is a general understanding of what electric fields are and how to describe an electric field strength. What we're going to do is define electric potential energy and electric potential difference, and then we're going to describe the nature of the flow of charge. Now first I want to start off by describing something to you that is probably familiar already. On the diagram on the left, what we have is a big blue ball representing Earth and a small green one representing some object that is at a height h above Earth. Now what we know is gravitational potential energy is equal to the mass of this object, the acceleration due to gravity, and then multiplied by the height of that object. Now what you know is that if we increase the height of that object, what we're also doing is increasing its potential energy, its gravitational potential energy. Very similar to that, if we were to have a test charge at some distance from a larger charged sphere, what we're also going to have is electric potential energy. Now, just like gravitational potential energy, the distance r from the charged sphere to the test charge, if we increase that, we're also going to change the potential energy. So the point I'm trying to make is that the position of an object relative to Earth and the position of a test charge relative to a charged sphere is what is going to determine the potential energies, either gravitational or electric in those cases. Now here what I've set up are charged plates, positively charged ones on top and negatively charged ones on the bottom. Now these charged plates are just flat surfaces that are charged, and the electric field are shown through the blue arrows coming out of the positive side and going towards the negative side. Now what we are going to demonstrate is that if we placed a test charge, we'll call it test charge Q prime, at this position, position 1, if we wanted to raise this test charge to a different position, let's say this position, position 2, now we're going to have to do some work to bring this test charge from this location to the next location. This is very similar to the work you have to do to lift an object from a lower height to a higher height. Now the amount of work that you do we'll call WQ prime, so the work done on Q prime to change its distance. And if we divide it by the value of the charge of that little test charge, then what we're going to define is what we're calling delta V, and delta V is the electric potential difference. Now another way to talk about potential difference is instead of placing a charge within an electric field, what we're going to do is choose 2 points. Now these 2 green points are not charges like they were in the purple one. These are just 2 points. Point number 1, point number 2, and these 2 points exist in some electric field with electric field strength E. Now if we knew the electric field strength, how strong is this electric field, and we multiplied it by the distance between these 2 points, then what we're also defining is delta V, the potential difference. Now what you should notice by now is that the potential difference is always going to be a comparison between 2 points, point 1 and point 2. Whether a test charge exists at point 1 and you're changing that by doing work, or you're just choosing 2 points where you want to compare the potentials between them to find the potential difference. Now delta V is the symbol for potential difference, and its unit is volts. Volts may be a familiar word to you because you've seen it in 5-volt batteries, 12-volt batteries. Depending on what country you're in, your power outlets at home have 220 volts or 110 volts. And all that really means is it's comparing the differences of electric potential energy between the 2 terminals, the plus side and the minus side. So the plus side on a battery and the minus side on the battery represent these positively charged plates, the negatively charged plates, And the 5 volts just means that the potential difference between them comes out to be 5 or 12 or 220 or 110. Now what we're going to do is talk about the flow of charge, but first we're going to use an analogy of water flowing because that's more real life to us. Now what I've set up is a bucket of water at position 1, and it's at some height from the ground, and because of this height it has a potential energy amount equal to mass times gravity and times height. The bucket number 2 has no height and therefore it has no potential energy. Now it doesn't show that it's on the floor, but we're going to say that it's on the floor and its potential energy is 0. Now if we just stared at this, nothing would happen. We'd have 2 buckets. It would be pretty boring. But if we were to connect these 2 buckets with some sort of pipe and we allowed the water to flow, we'll get eventually the second bucket to fill up with some water, and the bucket from position 1 would just empty up. Now the point that I'm trying to make is that the direction of flow of the water goes from higher potential energy towards a position of lower potential energy. And this is always going to be the case. Water always flows downwards. The only way you can get water to flow upwards is if you were to input some energy. Now we're not inputting energy here, we're just allowing it to flow. So the conclusion is water flows from higher potential positions to lower potential positions. Pretty easy to accept that. Now let's talk about charges. So over here I have a positively charged object and a negatively charged object. We're calling the positively charged object higher potential, and the one that's down here lower potential. Now this is higher potential not because it's higher up or above the other one, it's just higher potential because it has more charge. Now again, if we stared at this, these 2 objects are separate, nothing is happening. Nothing will happen unless we connect these 2 objects with some sort of conductor. So this black line here is a conducting material, some sort of metal or anything that can conduct charge. Naturally, you could probably guess what would happen. The charges would flow from the higher potential position to the lower potential position. So what you can imagine is that the charges will go through the conductor and leak down all the way to the lower potential, almost as if it's water entering a pipe going down to a lower position. Now this analogy helps a lot of people understand how the flow of charge happens. It's not flowing downwards because of gravity or anything like that. It's flowing downwards because it wants to go to lower potential from the higher potential that it came from. Now to summarize, a charged object will have electric potential energy based on its position relative to another charge. This is like having potential energy relative to the planet Earth. Based on your position, you have a potential energy, and charged objects behave the same way. The second point is that electric potential difference between 2 points is basically a comparison of the 2 points' electric potential energies. Now there are 2 ways to calculate it. The first way is to find out how much work you've done on the charge to move it and divide it by how much charge that test charge has. Another way is to multiply the strength of the electric field and multiply it by the distance of the 2 points that you want to find the potential differences between. And lastly, for the final point, charge will flow from higher potential to lower potential. Kind of a quick video. If you have any questions, shoot them at me. Otherwise, thanks for watching.